We're looking at vertical and horizontal asymptotes, and we just defined what they were. How do you find the vertical asymptotes? These are values of x that set the denominator equals 0, but not also the numerator. Horizontal asymptotes, they really depend on the degree of the numerator and the degree of the denominator. So you have, let's say, some function f of x is equal to, I don't know, a of x over b of x. Let's say that the degree of the numerator of a of x, that function, let's say is r, and the degree of the numerator, well, that was the numerator, denominator b of x is t. So there's three things that could happen. So case one, let me just move this over here. Why aren't you doing that? So one, that our numerator, the degree of the numerator, r, is bigger than the degree of the denominator, and we called it t. If that is the case, the degree of the numerator is bigger, then there's no horizontal asymptote. If the degree of the denominator is bigger, so t is bigger than r, then we have a horizontal asymptote, and the horizontal asymptote is at y equals a over b, where a is the leading coefficient of the numerator.
Professor, what does it say under horizontal asymptote?
Yeah, horizontal. So right here, where t is bigger than r. Oh, over here, or over here, where it says f of x is equal to a of x, some function a of x over some function b of x. And the degree of a of x, so that degrees, recall, are the power, the highest power of that polynomial, that exponent. So for instance, if I had 2x squared minus 1, my degree in this case is 2 because of the square. Where if I had y equals 7x to the 5th minus 4x to the 4th, the degree, the highest power would be 5. So we have to look at if we have a rational function like this, a horizontal asymptote could occur. There's three different possibilities. It all depends on the degree of the numerator denominator. If they're the same, then it's going to be y equals the leading coefficient of the top divided by the leading coefficient of the bottom. And b is the leading coefficient of the denominator. So recall, leading coefficients, those were the numbers in front of the variable that had the highest exponent. And then there's a last case scenario where 3, the degree of the denominator, which was t, Oops, sorry, that's if they were equal together. Let's just change that to equals now. That second one should be equals when I did that. And the last case is if the denominator is bigger than the numerator. If so, there is a horizontal asymptote, and it is the x-axis, which is the line y equals 0. So one of those cases will hold if you have a rational function. We're going to look at the degree of the numerator, degree of the denominator, determine which case holds, and then depending on that, depends on if there's a horizontal asymptote and where it goes. So there's a question here, vertical asymptotes. Is this true or false? If you have a function, f of x equals blah, 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 doesn't really matter what's up there, all over x minus a, then there must be a vertical asymptote at x equals a. So do you think that's true or false? If you think it's true, how about thumbs up? If you think that's false, thumbs down. Okay, so many thumbs up, agreeing that they think you guys believe that this is true, that a vertical asymptote would occur at x equals a, because a sets that denominator equals 0. We have to be careful though, because this could be false. It only occurs if the value sets the denominator equal to 0 and not also the numerator. And because I don't know what's up here, this blah, 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 it could have a factor of x minus a. So I'm going to say false, because it is possible. Or let's just say because, let's say, because the numerator could also set the numerator equals to 0. Could also set numerator could also be 0. How about that? Okay, so next example. So use the function f of x equals x squared plus 2x minus 8 all over the quantity x squared plus x minus 12 to answer the following questions. So identify all the vertical asymptotes. So when I'm identifying my vertical asymptotes, it's only going to occur if I have a rational function, so quotient here. And we always want to factor both the numerator and the denominator. So if I factor that numerator, I can say, well, f of x is equal to, it's a trinomial, 3 terms. So I'm looking at my coefficient in front of the x squared is 1. So I'm looking at what multiplies to -8, but adds to give me that middle coefficient 2. So that would be a +4 and a -2. So x plus 4, x minus 2 are the factors. All over, and denominator is also trinomial. Coefficient in front of x squared is 1, so it's the easier case. So we're looking at what multiplies to give us the constant -12 and adds to give us the middle coefficient 1. So multiplies to 12, adds to +1. So I know 4 and 3, it's adding to a positive, so it's going to be +4 and -3, so x minus 3. Okay, so it's undefined. Our domain are all values of x, which this is true. Where it's defined, we get a value back for y. This is undefined at x equals values which set the denominator equals 0. So -4 would set that denominator equal to 0, and x equals +3. There's different things happening at those values where it's undefined though. So if you look at this, x plus 4, those factors are common in the numerator denominator. So that's not a vertical asymptote. So at x equals -4, this is actually an open circle. We'll talk about that this could be a removable discontinuity in a little bit. But x equals 3, this one sets the denominator equals 0, but not also the numerator. So we have a vertical asymptote vertical asymptotes are a line. And so remember, vertical lines are always in the form x equals that number. So don't just say 3, because that's technically wrong. You want to say x equals 3. Okay, so there was a case where two values set the denominator equals 0. One was a vertical asymptote and one was not. Okay, so we know there's a vertical asymptote at x equals 3. That means that the graph is either going to be shooting up to positive infinity or negative infinity as we get closer and closer to x equals 3 on the left and or right, or well, both of them. And so number 2 says evaluate the limit as x approaches 3 on the left-hand side of f of x. So what we basically need to do is plug in numbers as x is approaching 3 on the left, and we want to see, is that going to be a positive number or a negative number? If it's positive, then that means it's shooting up to positive infinity. And if it's negative, then that means it's shooting down to negative infinity. So if I chose numbers to the left of 3 that are getting close, maybe look at what is f of 2.9. So if I plug this back in here, I want to see, am I going to get back a positive number or a negative number? So maybe we should go to Desmos and then pull up the feature where we can just start plugging in numbers and looking at it. Okay, so we're defining our function into Desmos. And so we have f of x is equal to, so I have a numerator and I have more than one term in the numerator. So you need to make sure you have put parentheses around that whole numerator. And the first term in there was x squared. So x squared. And then I had plus 2x minus 8, plus 2x minus 8. I'm going to get outside of the parentheses, close it. I'm going to put divided by, I should put me down into the denominator. Now I'm going to define the denominator, which was x squared plus x minus 12. So we defined our function. I'm going to push enter. And now I'm going to plug in, I want it to plug in 2.9 wherever I see an x. So f of 2.9 in here, notice you get -9. So to me, I know that this is going down to negative infinity, but let me show you. Let's even get closer to 3 on the left. So if we plug in f of 2.99, which is even closer to 3, notice I get -99. So if I even get closer, 2.999999, notice I get -9,999,999. So I can see as x's are getting closer and closer to 3 on the left, that's shooting down to negative infinity. Part 3 wanted to know what is the limit as x is approaching 3 on the right. So that's plugging in values bigger than 3, but close to it. So let's look at f of 3.1. I notice that's a positive number. So I notice that any number I plug in to the left of 3 that's close to that is actually gonna, and the closer I get to 3, it's gonna blow up. So let's see, f of 3.01, which is even closer to the 3, and that gives me 101. If I had put f of 3.00001, notice I get 100,001. So notice as I'm getting closer and closer to 3 on the right, that number's not, y value is not going to any particular number. It's either getting very, very small, going to negative infinity, or getting huge, going to positive infinity. Let me take that same function that we just defined. I'm going to copy it, and then let's go over and look at this, graphing it. So if I graph this function, notice that at 3, and we saw this, as x was approaching 3 on the left, we were shooting down to negative infinity. And here 3 on the right, it's shooting up to positive infinity. And so you can see right now by looking at this, you can tell that there's a horizontal asymptote. So let's just look at it now while we have the graph up. So notice as x is going to negative infinity, look at that line. It looks like it's getting closer and closer to your y value here of 1, right? As we go further and further, still it looks like a horizontal line. It's getting closer and closer, it looks like, to 1. Let me pull it over here on the other side of x equals 3. So also looks like there's a horizontal asymptote. And so as x is going to positive infinity, notice that graph looks like that y value it's getting closer and closer to is 1. So it looks like there's a horizontal asymptote at 1, but let's also show that algebraically. Okay, so horizontal asymptote, those are the end behaviors of what's going on with a graph. What does the y value approach as x approaches negative infinity and positive infinity? Does it approach a specific number, or is it growing without bounds? Well, like I told you, there's 3 different cases depending on an vertical asymptote, horizontal asymptote. So if the denominator, that's the one with a higher exponent, higher degree, if the denominator grows faster than the numerator, then the vertical asymptote goes to 0. And I'm sorry, I just said vertical asymptote, I meant horizontal asymptote. If the numerator and denominator grows just as fast, I really don't like this. I'm going to say it's not necessarily equal to 1. In our case, it does, because our leading coefficient on the top and the bottom were both 1. But really, the horizontal asymptote is going to occur at a over b, depending on what the leading coefficient at the top is and the bottom. So a over b, again, leading coefficient of top over leading coefficient of the bottom. And then the last case scenario, if the numerator has a higher power, it's growing much faster than the denominator, then we say that there is no horizontal asymptote, and that end behavior of the graph is going to shoot off to positive or negative infinity. So if you had looked at this example f of x, so the limit as x goes to infinity of that original function that we were looking at, let's say x squared plus 2x minus 8, all over x squared plus x minus 12. So the degree of the numerator is 2. And the degree of the denominator is 2. Those are the highest exponent of all those terms in either the numerator or the denominator. So they're the same. So look at the leading coefficient of the top. So the number in front of the x squared, it's not shown, so it's a 1. And the leading coefficient of the bottom is also 1. So we have a horizontal asymptote at y equals 1 over 1, which is 1. Okay, so if we have a rational function, it's helpful to know, is the function in the numerator growing faster or the function in the denominator growing faster? And so the next page of the notes kind of bring that, looking at the cases and realizing. So if you had these functions and you plugged in these values for x, you can see which one would be growing faster. If we looked at x squared, x cubed, and x to the 10th, I know x to the 10th, the higher power, is going to be growing at a much faster rate. The exponential piece, though, it depends on the base. So this is going to be growing and going off to infinity, and this is actually going to go faster than the base being x. So let's just plug in some points. So if you plug in 1 wherever you see an x squared, 1 squared is 1. If you plug in 10 wherever you see an x squared, well, 10 times 10 is 100, right? 100, we'd have 4 zeros. So that's 10,000, and 1,000 squared, we'd have 6 zeros. Is 1, did I do too many? I did 1 too many. Is 1 million. If you plugged in 1 into the cubed, well, 1 cubed is 1. Let's just go down here. 1 to the 10th is 1. 2 to the first power is 2. E to the first power is just e. 4 to the first power is 4. Natural log of 1. So this is saying e to what power? Remember, logs are exponents. E to what power gives us back 1? So recall, a number other than 0 raised to the 0 power is 1. So this would be 0. So now plug in 10, cube it. So 10 cubed, I'd have 3 zeros. This one's growing faster, right? I get 1,000 versus 100. 10 to the 10th, well, 10 times 10, 10 times, right? This is going to be, that's a lot of zeros, 10 zeros. And 2 to the 10th, well, that's 2 times 2 times 2, and you're multiplying 2 to its by itself 10 times. That gives us 1,024. If I take e and I take that and raise it to the 10th power, I get back approximately 22,000, 26.5. If I took 4 to the 10th, I get 1,048,576. And if I take the natural log of 10, so e to what power gives me 10? So approximately 2.3. So we would do the same thing, plugging in 100. Some of these are going to get obscenely really large. Um, so 100 cubed, that gives us 1 million. Okay, how about 100 to the 10th? We can, because this is really, really large, remember we could write things in terms of scientific notation. So we don't want to write all those zeros, right? So this is the same thing as 1 times 10 to the 20th power. Basically, I'd have 20 zeros after that 1. If I do 2 to the 100th, this gives me Spitzback scientific notation. So I'm going to round it. So 1.27 times 10 to the 30th. Okay, so that has more zeros than the one above. I know e to the 100th, that's even going to be bigger because e is approximately 2.8, and then base above was 2. So e to the 100th, 2.688 times 10 to the 43rd power. So I can tell right here, looking at this, the largest one that it's going to be. So rank fastest to slowest. You can see that the first one is going to be 4 to the x. And then it's going to be, second one is e to the x, third one, fourth, fifth, sixth. Natural log is going to probably be the slowest one. So the natural log, if I put in here of 100. So it's e to what power gives me back 100. So 2.18 raised to what power is about 100. And this is 4.61 about. Okay, so this is the slowest of the ranking, so 7. So looking at the horizontal asymptotes of these rational functions, gotta look at the degree, which is growing faster, numerator, denominator. If I look at the number 4, y equals x squared plus 4, that quantity all over the quantity 3x minus 5. The degree in the numerator is larger, so it's growing faster. And so if the numerator grows faster, there's no horizontal asymptote, and it shoots off to positive or negative infinity, depending on which way. Degree of the numerator is larger. So no horizontal asymptote. If you look at number 5, the quantity x plus 4, all over the quantity 3x minus 5. The degrees are the same. So the exponent, highest exponent in the numerator is 1, highest exponent in the denominator is 1. So it's the leading coefficient of the numerator, so the number in front of the x there is 1, all over the leading coefficient of the denominator. So the coefficient, the number in front of the x in that case is 3. So we would have a horizontal asymptote at y equals 1/3. And the last case scenario, we have y equals x plus 4 all over the quantity 3x squared minus 5. The degree of the denominator is larger, so it's growing faster. And so we have a horizontal asymptote. If the denominator is growing faster than the numerator, in the long run, that's going off to 0. So y equals 0. is the horizontal asymptote. Okay, so we'll look at Thursday, looking at limits going off to positive and negative infinity, using some of those facts of which grows faster sooner to find those asymptotes.